this module we will study degrees of freedom or kinematic indeterminacy. The outline of this module is we'll discuss about static indeterminacy, kinematic indeterminacy, and then we'll define degrees of freedom, and we'll formulate the stiffness matrix for a given structure, and then like wherever mass is not associated to any degree of freedom, so how to remove those degrees of freedom. So these things we will study in this module. First, what is static indeterminacy? So as we all know that we have three equations of equilibrium. So that is, sum of all forces in horizontal direction must be equal to 0, and sum of all vertical forces should be equal to 0, and sum of all moments should be equal to 0. So these are three equations of equilibrium in static condition. So static indeterminacy means number of forces or reactions that cannot be determined using the equations of static equilibrium. So for example, so if I take a simply supported beam, here hinge is there and a roller is there. So roller is vertical reaction comes here, and here vertical reaction as well as horizontal reaction comes. So three unknown reactions are there, and we have three equations of equilibrium. Sigma h is equal to 0, sigma v is equal to 0, sigma m is equal to 0. So that means it is statically determinate structure. Now, whereas if we take a fixed beam, so we have vertical reaction, horizontal reaction and a moment. Again vertical reaction here, horizontal reaction here and moment. So here three unknowns are there here and three unknowns here. Total 6 unknowns are there, but we have three equations of equilibrium. Three equations, 6 unknowns. So this is statically indeterminate structure. So this is called static indeterminacy. Degree is 3. Now it comes to kinematic indeterminacy. What is kinematic indeterminacy? So it is sum of degrees of freedom of the nodes, and then sum all the degrees of freedom of the nodes and then subtract those degrees of freedom that are constrained. So it is something like, say I have a frame. In this, so 1, 2, 3, 4. 4 nodes are there, 4 nodes. So 4 nodes in 2D plane frame structure, each node will have 3 degrees of freedom. So 4 nodes into 3 degrees of freedom, so that will make 12. And from this we need to subtract those degrees of freedom that are constrained. So in this, 3 here at the base are constrained, 3 on the other right side support are constrained. So that means 6 are constrained, so we can remove. So this structure can be 6 degrees of freedom structure. So this frame can be 6 degrees of freedom frame. 6 degrees of freedom are required to represent the system's behavior or structure's behavior. So in 2-dimensional structure we will have 3 degrees of freedom at each node, and whereas 3-dimensional structure we will have 6 degrees of freedom at each node. Now how do we calculate a stiffness of the member which is required for finding out the stiffness of the structure or frame? So here we have like 1 unit rotation. So a figure is shown on the slide. If I say take this a member and fix it on one side and apply rotation on another side. If I apply rotation on one side, the moment required to produce 1 unit rotation at this end, whereas the far end is fixed. The stiffness coefficient required is 4 EI by L, and half of that moment is transferred to the other end, 2 EI by L. And if the far end is fixed and if we are applying 1 unit rotation at this end, so if the far end is not fixed, it is hinged, so then we need 3 EI by L. So here if the far end is fixed, we need 4 EI by L and the moment transfer to this one or the carryover is 2 EI by L. So 4 EI by L and 2 EI by L both are in the same direction, that is anti-clockwise moment, anti-clockwise rotation, both to put together will give us 6 EI by L total anti-clockwise rotation. But for maintaining the equilibrium of the member, we need to give a couple, or the couple is developed at the two ends. So 6 EI by L anti-clockwise rotation must be balanced by 6 EI by L square force with a lever arm of length. That means here you can see 6 EI by L square on the right side downward force and 6 EI by L square on left side upward force. So that will give a balanced force to this 1 unit rotation, 1 unit rotation. And when it comes to hinged, okay, where far end is hinged, so we are giving 3 EI by L. As far end is hinged, at hinge location there will not be any moment, so that's why the total unbalanced moment is 3 EI by L, and the reactions or the couple what will form with that is 3 EI by L square. So 3 EI by L square downward on the right end and 3 EI by L square upward on the left end. So this is calculation of the stiffness coefficients when 1 unit rotation is given to one end of the member. Now when it comes to 1 unit deflection given at one end of the member, as you can see here, like a member where far end is fixed and the near end is rigid. So to that we are giving 1 unit displacement. Because of this 1 unit displacement, to maintain 0 angle here, a rotation have to be applied. So that rotation value is 6 EI by L square, and the same rotation need to be applied on the other end also, 6 EI by L square, to maintain this position. And 6 EI by L square and 6 EI by L square together is 12 EI by L square unbalanced moment. To balance this we need to apply clockwise couple. Okay, so that will be 12 EI by L cube on the right end downward and 12 EI by L cube on the left side support upward. So that will make the whole member in equilibrium. And the next one is like 1 unit displacement with a far end hinged. So there you need to apply a rotation of a moment of 3 EI by L square on the right side, and on the left side that is a hinge support, so moment is not needed there. So total unbalanced moment will be 3 EI by L square. So unbalanced moment is 3 EI by L, then couple with forces 3 EI by L square on the right side downward and 3 EI by L square on the left side upwards. Now let us develop a stiffness matrix for a given structure, given plane frame structure. In this you can see like beam is having length L and height of the column is H. EIC is given, this is flexural rigidity of column, and flexural rigidity of column 1 and column 2 both are same, and flexural rigidity of beam EIB is given, and a force is applied at this level, at the roof level. So in this one the degrees of freedom are 6. So how these degrees of freedom are 6? They are like 4 nodes are there, 1, 2, 3 and 4 nodes are there. So each node will have 3 degrees of freedom. So 4 into 3, 12 minus the sum of the reactions if you remove. So that will become 6 degrees of freedom system. So let's look at some special cases in this one. So EIB, that flexural rigidity of this beam, if it is infinity, so what is going to happen? So if flexural rigidity of this beam is infinity, then the reaction coming from one column, or the force required to produce 1 unit deflection at the tip of the column or the end of the column is 12 EI by L cube, that is H cube. So 2 columns are there. So 2 columns means column 1, column 2. So that will give us 24 EI by H cube. So in this one, what given condition is flexural rigidity of the column is infinity. So in that case what happens? It behaves like this. So this is 1 unit displacement, 1 unit displacement. So this will be 6 EI by h square, here 6 EI by h square, here 6 EI by h square, here 6 EI by h square. So this anti-clockwise 6 EI by h square, anti-clockwise 6 EI by h square. So we need to apply clockwise couple, that is 12 EI by h cube, and here also same 12 EI by h cube. So this 12 EI by h cube, 12 EI by h cube together we will get 24 EI by h cube. This is the combined stiffness of all the means both the columns. So that is when flexural rigidity is infinite. So rigid, if the slab is rigid, beam is rigid, then we can go for this condition. Okay, and on the other hand, if say there is no flexural rigidity, so it is 0. So in that case, so what is going to happen? So in that case, stiffness is 3 EI by h cube is the stiffness offered by one column. So it is something like this. So force applied. So this will be for 1 unit deflection. Okay, that stiffness coefficient is 3 EI by h cube. So 2 columns are there. So that force will be 6 EI by h cube. So EIB, that is flexural rigidity of beam is 0, is one extreme. Flexural rigidity of beam is infinity, this is another extreme. But usual cases it is neither 0 nor infinity, but usual cases it is somewhere in between. So if it is somewhere in between, so how do we develop stiffness matrix? So that is what we are going to see in this slide. As you can see here, okay, let me explain you this 6 degrees of freedom I told you in this previous slide. Now if I come to this slide, so degrees of freedom are 3 only. So 3 degrees of freedom at this node and 3 degrees of freedom at the right node. So if I take these 3 degrees and 3 degrees, it's something like this: 1, 2 and 3 degrees of freedom, and 1, 2 and 3 degrees of freedom. So 1, 2, 3, 4, 5, 6. So how this has become 3 degrees of freedom? It is like axial extension of columns are neglected. So that will leave this degrees of freedom 2, degree of freedom 5. So that will leave 1. Total 6 degrees of freedom will become 4 degrees of freedom. Rotation 3 will be there and rotation 6 will be there. And this translation, that is one translation degree of freedom 1 and translation degree of freedom 4, both are one and the same. So there is no axial compression or extension in the beam itself. Okay, so that will make these two as 1 only. So the total number of degrees of freedom will be 3 degrees of freedom. So 3 degrees of freedom structure will have, like if we have to develop a stiffness matrix for this, 3 degrees of freedom means we will get 3 by 3 matrix. So let us discuss how this matrix can be developed. So in this, the condition given is length of the beam is equal to 2 times height, and moment of inertia of beam is equal to moment of inertia of column. Both are same. So in that case, how do we develop this stiffness matrix? The first case is like give 1 unit displacement to 1 degree of freedom, and rest 2 degrees of freedom should be restrained, and force required to maintain this system is a stiffness element. If we write say U1 is equal to 1, U2 is equal to 0 and U3 is equal to 0, in that case, so if we write this, so U1 is 1. So that means degree of freedom 1 is given unit displacement, as you can see here. So degree of freedom 1, U1 is translation, U2 is rotation and U3 is also rotation. So U1 translation is given 1 unit. So 1 unit. So that means structure is moving up to this. So that means what it is essentially converts structure like this: 1 unit here, 1 unit here. Okay, so this. So that means this, the moment required here is 6 EI column by 6 EI by H square, and this 6 EI column by H square, here 6 EI by H square column, here 6 EI column by H square. So this 6 EI by H square, 6 EI by H square together will create unbalanced moment of 12 EI by H square, 12 EI by H cube. So that is in this direction, 12 EI by H cube column moment of inertia, and this reaction is also 12 EI by H cube. Similarly on the other side. So now we need to write the forces at this degree of freedom level. So we have U1, U2, U3 degrees of freedom. So let's write stiffness coefficients. What is K11? So K11 will be 24 EI column by H cube. This is first coefficient. K21. K21. So 2 is this one. So that means 6 EI column by H square, and K31 is 6 EI column by H square. So that completes first column of stiffness matrix. Now let's go to the second column. So how do we generate second column of stiffness matrix? Second column can be like U1 is 0, U2 is 1, and U3 is 0. So in this case it is something like this. So U2 is 1 unit rotation. So give 1 unit rotation to this joint. So it is something like this. And here 1 unit anticlockwise rotation. So when we give 1 unit anticlockwise rotation here, something like this. So where far end is fixed, how much is needed, how much moment is needed if you look at only beam. So it is 4 EI beam by length, and here 4 EI column by H, and here 2 EI beam by L, and here 2 EI column by H. So these are the forces which will act. Now if we develop stiffness coefficients from this one, K12 is equal to K22, K32, K12, K22, K32. So K12 is, so this is anticlockwise moment here. So this is anticlockwise here, anticlockwise here. So this is a beam reaction, beam moment. So this is 4 EI by H square, 4 EI by H and 2 EI by H together it will be 6 EI by H unbalanced. So we need to produce a force which is 6 EI column by H square. So it will be K12 is 6 EI column by H square, and K22 is the addition of these two moments, 4 EI column by H plus 4 EI beam by L, and K32 is 2 EI beam by L. So this is the second column of stiffness matrix, and the third column we can construct by U1 is equal to 0, U2 is equal to 0, and U3 is equal to 1. So here in this case we will do it similar operations. So U3 is this one. So 1 unit anticlockwise rotation here. So it behaves like this and it rotates like this. For rotating this 1 unit rotation, for making 1 unit rotation in the column, we need 4 EI column by height of the column. So that is H square, and 4 EI column by H, and here 4 EI beam by L, and half of that will be transferred here, that is 2 EI beam by L, and column 1 will transfer half, that is 2 EI column by H. So the unbalanced moment at this column is 4 EI column by H and 2 EI column by H together will be 6 EI column by H square, here 6 EI column by H square. So now if we write the coefficients K13, K23 and K33. So K13 is, that is 6 EI column by H square, and K23 is 2 EI beam by L, and K33 is 4 EI beam by L plus 4 EI column by H. So this constitutes stiffness matrix. So K11, K21, K31, K12, K22, K32, K31, K32, K33. Okay. So this is how we can form the stiffness matrix, and now you can see by using L is equal to 2H and moment of inertia of column is equal to moment of inertia of beam. So upon simplification, the total 3 by 3 matrix is this. Now after after generating the stiffness matrix, if there are no forces associated with the degrees of freedom available, it is something like this. You can see in this one, the degrees of freedom is here, degree of freedom is here, rotation is here, and translation. So translation means entire mass is concentrated at this one. So that means translational degree of freedom, that is degree of freedom 1, has mass associated with it, but degree of freedom 2 has 0 mass and degree of freedom 3 has 0 mass. So in this situation, how do we remove unwanted degrees of freedom from the equation? So that is what is required to be discussed. So it is something like this. So stiffness Ku is equal to F. So K has all elements in it, but displacement need to be found out, but F is only applied only at one place. So whereas these 2 degrees of freedom, so rotation there is no force applied, so that means force is applied only in the translational direction. So that means we need to remove unwanted degrees of freedom for simplification of solution. So how do we remove these unwanted degrees of freedom? These unwanted degrees of freedom can be removed in different methods. So that is by static condensation or elimination method. So there are these 2 methods. Static condensation method also can be used, or elimination method also can be used. So what is this method? Let us discuss. Now if you can see this one. So if I take this equation, so like let's make this as say some constant C. Okay. So 24 U1 plus 6H U2 plus 6H U3 is equal to Fs. 6H U1, I am writing simultaneous equations. 6H square U2 plus H square U3 is equal to 0. So 6H U1 plus H square U2 plus 6H square U3 is equal to 0. So we have force associated, force is applied only in one equation, whereas in these 2 equations it is 0. So it is better to substitute U2 and U3 in the form of U1. So like what we can do is we can formulate a matrix like this, say 6H square comma H square and 6H square multiply by U2 and U3 is equal to 6H Okay, u1, u1. Okay, so assuming that this is a known one, and we can find out u2 in terms of u1. So in this we can, in this manner we can eliminate and resubstitute in this one. So this is one method of eliminating it. There is another method which is called static condensation. So in this static condensation, the entire matrix can be divided into 4 parts. We can say this as A, this as B, this as C, and this as D. So this matrix can be like formulated like C is anyway there here. We can write this as C prime. So A minus C transpose D inverse B. Okay. So if we work out this matrix operation, okay, and then we will get only finally this equation. So that final equation will be that K equivalent is 96 by 7 into EI column by H cube. So this will be the equivalent stiffness after this matrix operation. In summary, what we have discussed in this module is degrees of freedom. First we discussed static indeterminacy, and second we discussed kinematic indeterminacy. So kinematic indeterminacy means number of independent degrees of freedom which are required for defining the system. So for example, something like this pendulum is there, only theta is needed for writing the displacement of this pendulum. So like L is fixed. If we have theta, we can say x and y coordinates of the system at any point of time. So like that, this has single degree of freedom system. So if you take multi-story building, so multi-story building can be rightly represented in the n number of degrees of freedom. So each node will have in 3D frame, each node will have 6 degrees of freedom, and in 2D analysis we can take each node having 3 degrees of freedom. So we have also discussed how to formulate a stiffness matrix for one story frame. So that is a 3 by 3 matrix, and if mass is not associated to the degree of freedom, we have studied how to remove these unwanted degrees of freedom where mass is not associated by static condensation or elimination method.